In this section, we're going to look at some more complicated rate mechanisms, including some problems where we have to identify the rate determining step. Okay, so the rate law should be based on the rate determining step, which means rate is equal to K2 NOBR2 times NO. But again, this NOBR2 is an intermediate, so we can't measure this thing. We're not going to see it when we actually run this reaction. So we have to look at, okay, well, how do you make NOBR2? Well, you make NOBR2 by having the rate constant times NO collision in the first step times BR2 in the first step. Right? So what we typically do is we insert that into the spot where the intermediate was or should be, and then just multiply it out. We now have two NOs, so this becomes NO squared, and that's because all of these things are involved before the rate determining step, so they are all part of the rate law. A couple quick things. One is I'm not worried about the K1, K2 mess that starts to show up here. When you run this reaction, you are going to get one rate constant. Now, someone who is better trained than we are is going to be able to go back and see if they can figure out what the speeds of these steps would actually be, and they can use that to form predictions about how fast this reaction is going and how these steps work, but that's well beyond our level. The second thing is I realize there's a much easier way to do this, right? Which is, again, think about the last thing I said a minute ago. Anything involved before the rate determining step is going to be part of the rate law. So we could say, oh, well, this is our rate law. So NR is an ingredient, BR2 is an ingredient, NO is an ingredient. Again, this is an intermediate, doesn't count. So two NOs and a BR2, this should be second order in NO, first order in BR2. Sure enough, that's what we have. So if you just count up all of the reactants that exist for the rate determining step, that's going to be your rate law. And that's it. That's much easier, actually, than doing the math. So trying this one really quick. I try to get away from using numbers, but I'm trying to say that this first one is clearly faster, the second step is clearly slower. Identify the intermediates, and then based on the rate determining step, see if you can determine the rate law. Okay, so do intermediates exist? Sure, N2O2, right? And so since this step is our slowest step, is our rate determining step, so our rate law should be rate is equal to K2 N2O2 times O2. But again, N2O2 is our intermediate, so we have to look at, well, how do you make that thing? Well, you make that thing with two NOs, so that would be the rate law for the first step. So we're going to insert this into the intermediate, and so that gives us the final rate law. Rate is equal to K NO squared times O2. Again, the reactants to get to the rate determining step are two NOs and an O2. Our rate law is NO squared and O2. So go ahead and try this one really quickly, and then we'll go through the answer in a second. All right. So again, our rate determining step, our slowest step, although not by much, is the second one. And so we could say, oh, okay, well, the collision between PO3 and PO1 should be our rate determining step. The only problem is that PO3 is an intermediate, so we can't use that to determine the rate law, or at least we need to figure out how we make that PO3, because that's going to influence the rate determining step. So we're going to make PO3 by using PO and O2. And so if we insert that into PO3, we end up with PO squared, O2 to the 1. Again, if you look at all the reactants involved into that rate determining step, we have two POs and O2. Our rate law is PO squared and O2. So here's where I point out that a lot of these rate laws are totally backwards, right? We are proposing a rate based on a mechanism. And really, in chemistry, what we do is we propose a mechanism based on the rate law. We do the experiment first, compare that to what we think is happening, and devise a way of explaining that mechanism afterwards. And so this problem is very backwards because we don't know how to propose a mechanism yet. Like, we are not there. Okay, so But these next couple problems get us a little closer to that environment. A mechanism has been believed to occur in two steps, where ozone reacts with NO2, and then NO3 that forms reacts with NO2 again to get the actual product. When we run the experiment, the rate law is found to be rate is equal to K, O3 to the 1, NO2 to the 1. So based on what you know, what step is the slowest? Which of these steps determines the rate? Okay, so if we say this first step is slow, right, that means that's the only collision that matters. So we get ozone and we get NO2, each are 1 to 1. That is the rate law they had in the question. So there we go, that's the right answer. Let's take a second, though, and look at the other possible answer, just because it's good practice. So if the second step is rate determining, then the collision that's important would be NO3 and NO2 colliding. Again, NO3 is an intermediate, so then we have to look at how we form that. That would involve ozone and NO2 colliding, so we'd have to insert that into the NO3, and then we get ozone to the 1, NO2 squared. Now that doesn't match what we wanted, so this is the wrong answer, but nonetheless it was good practice to walk through. Okay, so this is much more like what you'd have in the lab. We have all these ingredients that we added in piece by piece, but the rate law is found to be H2O2 to the 1, iodine to the 1, right? So is this a single step or a multi-step reaction? What kind of predictions can you make about where that rate determining step is going to be? And finally, what will happen if you add more H+, right? What effect will this happen? Again, really look closely at that rate law before you make a prediction. Okay, so is this a single step or a multi-step reaction? It has to be multi-step. Why? Because there are ingredients in this reaction. There are reactants that are not involved in the rate determining step, which means they have to be added somewhere after the rate determining step. So they're still important, but they're just part of one of those smaller hills that don't affect the reaction speed. So the first step would likely be hydrogen peroxide reacting with iodide to form something, right? And so we can make that prediction based on the rate law. It's possible that these could be two smaller steps, but it's much more likely that those two things are colliding to make something new. What effect will adding more H plus have? None. It's not part of the rate law, which means it's a zero order reactant. It's being added into this reaction after the rate determining step, so it is not important.